What I'm going to do next is we're going to start developing mathematical formulas for radiation patterns. We talked about them generally, but now we want to be specific in how we actually calculate them. But to do that, we have to use a little bit of spherical mathematics, which I'm not sure that if you've been exposed to previously or not. So I just need to take a tangent right now and describe something called the steradian. And so you're probably very familiar with the units of radians. We've been using them in this class very frequently, and we know that they're used to measure angles. More specifically, I have to say that they're used to measure angles in a plane, right? I am drawing on this piece of, on this tablet, therefore I am in, let's say, the XY plane. I want to measure an angle theta in the plane. I can say that is some sort of radian, right? That is what's called a plane angle. Your whole life you've just probably been calling that an angle, but more specifically it is a plane angle because there are other types of angles. Plane angles are typically measured in units of radians or degrees, but where did the units of radians come from? Why do those exist? Why are there 2 pi radians in a circle, for example? Well, 1 radian is mathematically defined as the angle formed when 2 radial lines are drawn from the center of a circle and the distance between the radial lines on the perimeter of the circle is equal to the radius. So this line is r, this line is r, this line is r. That angle right there is by definition 1 radian. More formally, we say 1 radian is defined as the plane angle with its vertex at the center of a circle with a radius r that is subtended by an arc whose length is r. So that's the definition of a radian. So now I want to move from a plane into a sphere, right? A 3-dimensional representation of a circle. So a steradian, S-T-E-R-A-D-I-A-N, a steradian is the solid angle with its vertex at the center of the sphere of radius r that is subtended by a spherical surface area that has a length equal to r squared. So that's a little bit difficult to understand, but basically we're saying that inside this circle, or inside the sphere, there's what's called a solid angle. And instead of being in 1 dimension, that angle's in, you got to kind of picture it in 2 dimensions. There's an angle in here. And that angle, is, if it's 1 steradian, is, well, how big is that kind of this cone that we've drawn such that the surface area of the cone on the radius of the sphere is equal to r squared. And that angle, that solid angle, is called a steradian. Since the area of a sphere is pi r squared, there are 4 pi steradians in a sphere. So in 1 sphere, there are 4 pi steradians. There are 2 pi radians in a circle. There are 4 pi steradians in a sphere. So this next part's always a little confusing for students. Don't worry about it too much, but I just kind of need to put it out there. If I were to take a differential surface area element on this sphere, I would call that ds. So this is just an infinitesimally small little surface area element. And in spherical coordinates, how can I determine the formula for the ds element in terms of the spherical coordinate systems? Well, it's going to be the radius squared of the sphere of whose surface I'm on. I'm going to take the sine of theta, and I'm going to say d theta d phi. This is a differential surface element. It's meter squared. So this is the formula for a small little differential surface element on the surface of a sphere. Don't worry if you don't understand where these come from. It's actually a pretty complex mathematical proof to show that. And unfortunately, I'm not a big fan of this method most times, but I'm just going to ask you to memorize this. This is the differential surface element on a sphere. We can also have a differential angle, differential solid angle inside. So you can imagine if I had a differential angle d theta, I can have a differential solid angle inside of the sphere, and we give that the notation d capital omega, and it is just ds divided by r squared, my differential surface element divided by r squared. So that just simplifies to sine theta d theta d phi. Right. And again, that one I think makes more sense. If not, Don't worry about it too much. Don't trouble yourself too much. Just memorize these values.